So a little bit more about TCP, UDP, and how they interact and send their messages back and forth to each other. I want to start this out though with a little bit of a demo to kind of transition us from talking about the transport layer in general and TCP, UDP in more detail. I mentioned before we can take a look on either Linux or Windows system and see what ports are being used, either TCP or UDP, for each application. So that's something I want to show you now. So what we can do is we'll bring up Netstat, and this will give you the list of all your TCP and UDP ports that are open on your system. So listening means there's some sort of service running on your computer that's waiting for connections. You may also have actual established connections. So established means, you know, it's an active connection being used for something. So the one on the left is your source, and the one on the right is your destination, essentially. So you have local and remote, and you also have not just the IP, but you have local and remote port, and that's really what we want to look at. So what we're going to do is this is our baseline essentially. So let's open up some browsers, and I'll open up Google. And then if we run this again, and we go look up, there we can see there's a whole bunch of Google here. Now I use Google with SSL, so that's why it says 443. But we can see my connections that are established to Google on 443, and there's several different servers we're connecting for Google, and that's the way they do things. But on the left side, you can see there's also individual processes within the browser that are listening for return traffic. So when we send a PDU from us to Google, so we're sending it as a source of this address with this port to a destination of this address with this port, it gets to their side, and then they have to address it back to us. That's how it finds out not just who to talk to on the server side, but then who to talk to on our client side. When Google sends the response, it's going to say, here's my source IP and port, and here's my destination IP and port, the reverse of what we sent them. So when they send it back to us, that data unit is going to have in its header information, it's going to say, here's the destination I'm trying to get to, and here's the destination port. That port then is associated to this running web browser. That's how that works. So that's how both the client and the server have their own ports, and the servers usually run on common, well-known ports, as we just discussed, but on the clients it's more of a randomly generated number, and depending on the operating system, sometimes these numbers can be overlap, which can cause problems, but usually you'll get a randomized number that's unique, at least for that slice of time. So this is how that works, and if we do another window and another window, and we run it again, you'll see that each browser window has additional ports that have been randomly assigned to it. So that's how, whenever you create a new tab, whenever you create a new window, that's how that works. It creates a randomized port on your side, so that when it sends its data unit to whatever server you're trying to talk to, it has some idea to how to get back to that application. So each application gets those randomized ports. Sometimes it's not randomized though, it depends on what you're using, but the web browsers are a good example of that, where it randomly generates a source port on your side of the client so that the server knows to send it back to us, and then our TCP IP stack can then send it to the correct application. It does that based off of these ports. So now that we're talking about TCP UDP a little bit more, let's talk about how it provides communications. So there's a couple different fields that are used, and I'll list these off here. Within the header information of a TCP UDP packet, we have some various optional fields, and some of those are urgent. Whoops. We have acknowledgement. We have push. There's reset, which you'll see when you have a problem. We have SYN, and then we have FIN. And we'll talk a little bit more about these. Urgent and push These two are used for urgently trying to get some sort of data to an application, and like for example, push will tell the TCP stack to send it to the application as fast as possible. It'll try and push it through the stack to take priority essentially. Acknowledgement is used constantly. We'll talk about that in a second. Reset is used to terminate a connection and reset it again, kind of like a force reset in a way. It's not really usually a clean way of resetting a connection. SYN brings up a connection and FIN terminates one nicely. So let's talk about how that works. So with the TCP, we have a three-way handshake to bring up a connection. So if we have a source computer and a destination computer, they're going to start out their communication by saying, I want to talk to destination. So I'm going to say SYN, and I'm going to send a SYN over to him. The destination is going to say, okay, yeah, I received that. That's fine. I'm going to send back to you a SYN with an ACK. And then the source is going to say, okay, yeah, that sounds good. I am talking to you. That's good. We're going to send back an ACK, and I'm going to acknowledge. So we're saying, let's bring up a connection. Okay, yeah, let's bring up a connection. I acknowledge you. Sure, I acknowledge you. Great. Now let's start talking. After that happens, then we're going to have data. And then there's going to be data for the application there. When we want to finish talking, we'll send, hopefully not a reset, we'll send a nice finishing four-way session teardown. So there's a three-way handshake to create the connection. There's like a four-way handshake essentially to terminate it cleanly. You can reset, which is the ugly way of doing it usually, but the clean way is doing it this way. So let's say we finished communicating, and we're going to say, we'll do it on the source side. It can be either side, depends on what application you're using and how much time has been spent idling or something like that. But let's say we finished our communication and the source application says, okay, good, we're done. So we're going to say FIN. We're going to finish our connection. He's going to say, okay, I acknowledge that, and he's going to send that back to us. We're going to say FIN. I want to finish your connection, and we're going to say ACK. I acknowledge that as well. So it makes you wonder why they didn't do FIN-ACK, but that's the way it is. So we have FIN-ACK, FIN-ACK, and then that closes out our connection. One thing to note about this is not just the difference of the three-way handshake and the four-way closure, but these are not packets really. These are options that are turned on in a communication. So let's take a look at that actually. It'll make more sense. So let's bring up Wireshark, and we're going to start capturing on one of my interfaces. We're going to close these out. So let's bring up a browser. And then we'll stop our communications here, get a little bit more room. Looks like I was talking to it here somewhere. Yeah, so what's nice with Wireshark is we can do this. We can right click on something and say follow TCP stream, which not only lets you see only those packets in that communication, but it also gives you a nice little output of the raw data, which is kind of nice. So let's take a look. There we go. Our first packet sent to the server, we said, hey, here we want to talk to you. Let's bring up a connection. There's our SYN. So you see how there says flags here? There's a series of different options, as I mentioned before: urgent, acknowledgement, push, reset, FIN, SYN. These are all bits that can be turned on in the header information when it's encapsulated. So remember before when we said we take the data and slice it up into segments, and then it gets information attached to either the header or the tail of that piece of data, that PDU. So this is where that comes from. So this is the header information that we're looking at here that is in front of the actual data payload. So in here we have a flag that's turned on. It's 1 bit, so it's just a 0 or a 1, and its position in that header, the TCP IP stack knows, you know, that's a SYN bit that's either on or off. If you looked at it in raw form, it would just be 0000000000010. So the TCP IP stack knows, oh, that 1, that's in the slot for SYN. So there we have the SYN turned on. In response, the server says, yeah, I'll talk to you. Let's do a SYN, and I'm going to acknowledge that, yeah, you did talk to me. So I acknowledge your SYN. Let's go ahead and SYN. I'm going to bring up my connection. We then in return say, yeah, sure, I acknowledge that. Let's start talking. We then start talking and sending our data. Now this is encrypted, so we're not really going to see anything. But if it were over port 80, we'd be able to take a look at some of the traffic that's actually sent. We have some basic TLS and HTTP traffic being sent here, where it brings up a connection. We send some information. We are still bringing up a connection here with TLS. We send some data back and forth to each other to show the web page. And then if we had kept recording, we could have seen the termination. Let me see if I can create a termination. Here's our traffic. We're going to bring up our website. You'll see that go flying through here. Here's all our application data. We're acknowledging. Look at all these different packets. Remember I said it can be amazing at how much goes on behind the scenes? We loaded one basic page, and look at all these packets that were sent and received. You should go do that when you open up msn.com or something like that. It's thousands of these that go to and from just to load your home page. So let's take a look at this. Let's see if we can find our fin here. There we go. Good. So now I've closed my browser, and the browser was the one that finished the connection because the server still had the connection open, and he was saying, "Hey, let's terminate our connection." So we sent fin. We said, "Okay, let's finish that." He said, "Sure, let's finish that. Well, I acknowledge you." And okay, let's acknowledge. So I've seen both. This one, interestingly, might be because it's a newer version or something like that, but it does finac. I've seen ones that are also fin and then a separate ACK and then fin and a separate ACK. That's why I drew it that way. But that's the termination sequence. So you have finac, ACK. So we'll close that out. I mentioned about the reassembly. So the TCP allows for reassembly of those segments. So if some of those were received out of order, it will reassemble them correctly when it gets to the to send it up to the application, so things aren't misaligned. So say you were watching a video or something like that and you were using TCP. If it were received out of order, then you might have jolty video of seeing frames that happened a few seconds ago and new frames that are happening now and things like that. This will reassemble it in correct order. So say you're watching something on YouTube, for example, and it's buffering. That buffering is being done with TCP to ensure that that traffic is properly rebuilt when it's in your browser. I mentioned flow control as well. So flow control is done through window size. And actually, let's bring that up too. Close that prematurely. So I mentioned that kind of like determines how fast things are communicating, but really it's the size of data that's sent and received. So we'll bring that up, and then we'll just close that out. And if we take a look in here, here's our window size. The window size defines how much data can be sent and received before an acknowledgement. So what happens really is this. We have, let me clear clear this out. What happens when you're sending and receiving all these packets of data is you'll do that three-way handshake. You'll say SYN, and then they'll say SYNAC, and then they'll say ACK, and then we'll start sending data, right? So as we start sending data, we're going to be sending, we'll say from the server, if this was our source and this was our destination, this is our server over here running a website on port 80, and then this is on port, 5976 or 781 or something like that. We're going to be receiving data from the server. So the server is going to say, all right, here's some data. So here's data, 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 and then at some point we're going to say, oh, okay, I acknowledge that I've received all those. And then he's going to say, cool, all right, here's more data, here's more data, here's more data, and then we're going to say, okay, yeah, I got all those. That right there is your window size. How much data is sent before you acknowledge it. That's really what it is. So a smaller window size means you're going to get more acknowledgments in between each time you send or data, which on an unreliable connection or an overloaded connection, you're going to want that, because if you lose one of those pieces of data and we don't acknowledge it, it's going to have to resend that entire window size. There's other ways around it, but that's basically the idea, in that we want to make it as efficient as possible so we don't have to send an acknowledgement for every single packet, but you want to send it for a few packets. You receive a few, then we'll send an acknowledgement. We don't have to waste our time acknowledging every single one. That's your window size. So the window size is how much data, how many packets are sent before you say, acknowledge, I received it. That's what your window size is. So this TCP allows the stack to communicate about what window size is acceptable. If we go through and look, you'll see the window size changes. So it'll negotiate a certain amount of window size. And actually you can see that here, application data, app data, app data, app data, and then we end up having an acknowledgement at some point, and then app data, app data, app data. That's really what's happening there. We also have the ability to tell it we need to get data. So let's say we missed something. So let's say this one we missed. There's an option, depending on what you're using, to do fast retransmit and recovery, which kind of is a way of harassing the other system to tell it that you need that extra data. So let's say this PDU was lost in the ether of the internet. Instead of waiting until it realizes that we didn't acknowledge that that was sent, we can immediately say, hey, retransmit that, man. Seriously, I need that. And if it doesn't send it, we can say, hey, retransmit that. Retransmit that. Come on, I need it. I need this. I need this. I need this right now. I need it. It's a way of harassing the system to say, give me that piece of data. I need it immediately. Fast retransmit and recovery allows you to do that. And a lot of modern systems do that now, modern TCP stacks. I mentioned UDP. So UDP doesn't really have any of this. It's pretty much connectionless. If you take a look at some of these, I'm sure there's some up here. There we got some DNS. DNS is UDP. There's no connection there. We did some queries to find out who the heck Google.com is. So we were saying, hey, who's Google? I need to find out. And then my router said, oh yeah, I know who Google is. Here's his IP address. So there we were saying, where's Google? That's Google. Who's Google? That's Google. But there's no connection there. Notice how there's no TCP handshake, there's no SYN, FIN, ACK, none of that. It's just here's my PDU for DNS, here's my PDU for DNS in return. And if I didn't receive it, if I didn't receive that response, I would have just queried again and said, hey, do you want to tell me who that is? It's not a very it's completely connectionless. It's not a very intelligent method of doing things, but it's very lightweight. See how it's just, here's what I need, here's my response, instead of saying, let's set up a giant connection here and then start sending my data. it's much smaller, much more lightweight, used for fast communications, things that don't necessarily need to have that sort of reliability. So if I had missed that DNS query response, it would have then my client would have just resent a query in a second later. So from here, we're going to talk a bit more about IP addresses and IPv4, and then we'll move into IPv6 and things like that, and we'll start talking about what these different IP addresses mean that you're seeing here, and the different properties of them, and what's inside the header. So we've taken a look at some of the TCP header. Let's go ahead and take a look at some of the IP header next.